Hey everybody, my name is Randall Karcher, and today I'm presenting on behalf of Goliath Resources on the updates of our Golddigger property, as well as the research that we've been doing therein. So here's the boilerplate statement, forward-looking. We're going to say some forward-looking stuff. So right here is the Golden Triangle of British Columbia. Seeing as this is Golden Triangle University, hopefully I don't have to tell you where this is. But we're located at the southern tip of the Golden Triangle down here. That's our Golddigger and Sherbet discovery down here. Our neighbors include Dolly Varden, Homestake, we're south of Red Mountain, and then the Porter Idaho mines. We have expanded our claim package in the last couple of years, especially towards the north and to the south here. We're just over 91,000 hectares now, and that is to accommodate new outcrop that is melting out of the Cambria ice fields up here near Treasure Island, as well as a large section of the Hyder Pluton down south. We'll get into why that's been an important acquisition later. Furthermore, we have a lot of the red line adjacent property as well, so that has been a part of our land acquisition strategy, as the red line, and then the new claims to the north and to the south. So we're going to talk mainly about Sherbet today. We have a new model update which includes 5 mineralized zones that we're intersecting in Sherbet Mountain. The style of mineralization found at Sherbet include vein-hosted occurrences. So these are polymetallic quartz sulfide veins with abundant visible gold, local silver, and then a variety of sulfides that we'll get into in just a second. These are controlled by structures of the Skeena fold and thrust belt primarily. So a structure at the contact between the Upper Hazelton volcanics and then overlying Upper Hazelton sedimentary rocks, and above that Bowser Lake sedimentary rocks. So we have a structure there that's hosting the Bonanza Zone here. Below that is Golden Gate. Those are large quartz veins inside of the andesite. And then in the folded strata above the volcanic rocks, that's where we're getting our Eldorado, Whopper, and then our Sherbet, which is the largest inside of those sedimentary rocks. And there's also a series of these gold-bearing granitoid dikes. They're locally gold-bearing with pretty reasonable grades. We'll touch on those more as well. So this right here on the left is a bird's eye view of Sherbet Mountain. This dashed black line right here is the outcrop of the Sherbet Zone, kind of shown here on the right in yellow. And then down here, that is the contact of the Bonanza Shear, which is marking roughly the contact between the andesites and the overlying sedimentary rocks. And all the red dots on these projected drill holes, those are occurrences of VG. So what we're really showing here is just the abundance of how much VG there is on the property. The vast majority of our drill holes, in fact, encounter VG. And as you can see here from the model, it's sort of a layer cake occurrence of these different vein zones, which helps further explain our hit rate on Sherbet Mountain being so phenomenally high. It's because you can commonly hit several different ore zones in one drill hole. And yeah, just the entire thing is peppered with VG, including these vein zones that we've already defined, as well as some zones that are just now coming into light that we'll be able to further define with more drilling. We have several different styles of mineralization found at Sherbet. So the first and most common of which in the sedimentary rocks are breccia zones. So just quartz vein networks of brittle breccia textures. Inside of these we have semi-massive to massive sulfide lenses, including dominantly pyrrhotite, sphalerite, galena, and then lesser chalcopyrite and pyrite. And then the gold is strongly associated in these veins with the sulfides. Down here, this is a sheared example of that breccia. This is more common towards the Bonanza Zone that we were touching on. These exist primarily in very strongly sheared rocks, and locally the veins themselves are sheared as well, with the same sulfide mineralogy that I've outlined. Down in those andesite-hosted veins, that's the Golden Gate style that I mentioned. These are more cohesive, single, more massive quartz veins, less brecciated textures, more just multi-meter long veins with sulfide lenses within, of course, all that VG. So these are fairly similar in their mineralogical composition. It's just texturally they're quite variable. Depending on where we're at in the system, the amount of sulfides change. We have less sphalerite and galena lower in the system in a lot of those drill intercepts. But that is a different style than what we're getting in these granitoid dikes. So our gold-bearing granitoid dikes are very sulfide poor, in fact. We have quartz veins that are centimetric, they're quite small, and strong calc-silicate and potassic alteration inside of these veined dikes. They're porphyritic, locally they're more equigranular, and this is where we're hosting gold grades that are commonly exceeding 10 grams per ton and are good intercepts. But instead of being associated with sulfides, there's actually a bismuth and bismuth telluride association that we're getting inside of these granitoid dikes. So here are some close-ups of the typical styles of mineralization. What we have here is pyrrhotite, sphalerite, galena with some chalcopyrite. These form along quartz grain boundaries and as fractures cutting through these quartz veins. Shown here is the abundance of coarse gold that we have locally in the system. So here's a ruler for scale, and inside of these red circles, there are multi-millimeter wide gold occurrences in there. So that is pretty common at Sherbet, is this really easy to see coarse gold. And then inside of these granitoids, we have very small centimetric quartz veinlets without the sulfides that I've previously mentioned, but instead occurring as composite grains of gold, native bismuth, and then other bismuth minerals. So we're going to dip our toes into the geochronology here. We touched a lot on this on the presentation last year, but we have some updates to the geochron which start to bring the story into clearer focus. So I'm going to start with the garnets, which I did outline last year. These are the earliest alteration assemblage found from the hydrothermal system responsible for gold mineralization. These are different from, say, metamorphic garnets. These are true hydrothermal garnets, so they're alteration minerals. And they are cut by subsequent sulfide and gold mineralization. As you can see here on the bottom left, we have these euhedral garnets that have fractures full of sulfide cutting right through. So we know that this is the oldest, older than our actual mineralization. We've actually recalculated the ages with a new common lead standard. Last year, the date that I presented was about 54 million years. Though we've reanalyzed these samples, now correcting for common lead, which was a problem inside of the first batch. And now actually it's a bit younger. It seems that these garnets are actually about 52.2 plus or minus 1.6 for the garnets that we sampled. We have these gold-bearing granitoid dikes that we also have a date on. So what we have here is a linearized probability diagram, and just to put it in English, this central population here is what's representing the zircons that most likely formed in the actual emplacement of the dike. This is going to be potentially early zircons that aren't representative of the emplacement age, and then these ones that fall off the slope here are likely due to lead loss. So what we're doing is taking a weighted average of these emplacement zircons for uranium lead dating, and that's what we have here on the right, and what we're getting is a date of 52.0 plus or minus 1.5 million years. And so these are for the dikes that are actually gold bearing, so it's in an agreement with our garnet dates. Finally, we also have molybdenite mineralization found inside of those dikes and rarely outside in the polymetallic quartz sulfide veins. We have 4 different samples of molybdenite that we did for rhenium osmium dating in the granitoid dikes, which is associated with the bismuth gold mineralization, like I said. And what we're finding here is a much tighter date of 52.14 plus or minus 1 million years. And hopefully you have those dates in your head. Just kidding, it's fine. I have them right here to just compare. So what we have is a very, very clean agreement between the garnets, the zircons, and the molybdenite, all showing that these are good indicators that this is an Eocene system. And they also agree quite nicely with a new bit of geochronology that was put out by the BCGS of the Hyder-Pluton just a couple of kilometers away. So our gold system is on the eastern flank of the Hyder-Pluton. Just a couple kilometers away, we have a TIMS uranium lead date of the Hyder at 51.9 million years with a very small margin of error, which is really noteworthy because it's likely that the dikes that we're seeing here are, I mean, they're definitely temporally close to the Hyder, and geochemically they're quite similar as well. So what we're seeing is an episode of magmatism related to the Hyder, which is likely what's driving the mineralization in the system. Furthermore, we also know that the metamorphic aureole of the Hyder Pluton, the rocks that have been baked nearby, are actually that is cross-cut by our gold mineralization. So the veins we know come in after the Hyder. So these dates are very, very tight, and we know that these are temporally linked. So to summarize all of that, the geochronology is fairly strongly showing us that it is an Eocene system. And the spatial and temporal relationships between the Hyder Pluton, which I've just discussed, and our gold bearing veins and related alteration suggest a link there to Eocene magmatism, specifically in the Hyder Pluton, which is largely overlooked so far in the Golden Triangle. We'll touch on that a little bit more later, but first we're going to dip into the geochemistry of these dikes that I've been talking about. So right here what we have is a correlation between the concentration of bismuth and gold inside of our auriferous dike intercepts. So we have a couple of different populations of dikes here represented by these different slopes. The first is the most gold-rich member of the granitoid dikes, followed by this slope right here, this black one with the stars. And then what we find is rarely the Hyder Pluton will also have gold-bearing veins with a slope right here, distinct from the dikes though. So these distinct trends may be suggesting multiple magmatic hydrothermal pulses off of the Hyder, perhaps as the magma chamber evolved, which is not too surprising for this sort of system, for an intrusion-related system. And this could be important for exploration going forward. Furthermore, the majority of the granitoid dikes that we find, they plot in the ilmenite series field. So that's for the magnetic susceptibility, the difference between magnetite or ilmenite. It's broadly how oxidized or reduced the magma is. And what we're finding is that especially the gold-bearing dikes are overwhelmingly found in the ilmenite series field. So they're hosted by the more reduced dikes found here. So that's important because we've established this to be an intrusion-related system related to moderately reduced magmas, though when you plot the magnetic susceptibility of these dikes, we have them right here about 0.5 to at most about 5. And this is a little figure from Hart where he outlines reduced intrusion-related gold systems typified by Fort Knox and Dublin Gulch right here, and other reduced magmatic systems, versus the Whitehorse copper, gold, silver, which is oxidized end member. And I don't have them plotted together here, but that range is right about here. So our magnetic susceptibility of these dikes don't plot cleanly within what would be typical of a reduced intrusion-related gold deposit model, but rather this is an intrusion-related system related to a moderately reduced fluid. So somewhere in between, an important distinction from that deposit model. It sort of demonstrates the difference between model-driven thinking and process-driven thinking there. So to summarize that, there are strong correlations between gold and bismuth, which are typical of intrusion-related systems and all magmatic hydrothermal systems with these trends. But the distinct slopes of the trends suggest that there could be multiple pulses. The actual dikes are moderately reduced in character, which is noteworthy, however, not exactly aligned with a typical Rierg type model. So now we're going to touch on the petrography which has been done. What we're finding with the actual stages of gold mineralization is that there's a early and a late stage, at least there's those two stages. So right here we have two micro photographs. This is actually the same vein, just once in, this one's in transmitted light, this one's in reflected light. And what we find is that the earliest alteration stage associated with gold is one dominated by calc-silicates. So this is an actinolite veinlet right here with a clinozoicite halo. They're calc-silicates, to put it more plainly. And we're finding that the gold is strongly associated with this we'd call retrograde calc-silicate stage, which is post-dating pyroxene and garnets. But yeah, there's still calc-silicates. So white here, you can see that the gold in yellow, of course, and then the silver mineral, those are bismuth and bismuth tellurides. We're finding a strong association between these two and the calc-silicate halo and this veinlet. Now this is taken in the andesite, not inside of those granitoid dikes. This is actually found in the andesite. We also have a later stage of gold mineralization that's associated with chlorite. So that is shown right here on the left. This is another reflected light image. We have fractures of chlorite and patches of chlorite replacing earlier pyroxene with gold very strongly spatially associated, entrained inside of those veinlets and associated with patches of chlorite alteration. This is found overprinting the calc-silicate stage. Well, we have another example here found on an SEM, the same veinlets of chlorite running through pyroxene here, though not shown in these images. They also overprint that actinolite that I was talking about. So why this is important is because it's demonstrating there are multiple stages of gold, and it turns out our highest grade is found where these stages are the high temperature is overprinted by the later lower temperature assemblage. So here's an example. This is the early assemblage found with a bunch of bismuth telluride and gold. On this previous slide right here, this chlorite veinlet is found in the same sample. This is hole 260. And yeah, there seems to be these zones on our property where we have both the high temperature early and then the late low temperature assemblages, and that's where our highest grade is found. So this is in the andesite with abundant calc-silicate alteration in quartz veins. This is a sample from this 260 interval that we're talking about now. Every one of these red circles is another occurrence of VG. And just to explain why that's so important, here is the Northern Miners top 20 intercepts that were published in 2025 specifically for gold mineralization. And that intercept in hole 260 was the 15th best hole reported by the Northern Miner. So this is a pretty big deal, this multi-stage gold mineralization, and it has implications for how to find more of this multi-stage, and it helps us spatially orient ourselves where we could be in the system. So to summarize all that, the gold occurred in multiple stages, and the highest grade at Golddigger is what is represented. But those multiple stages are represented as where we find those highest grades. So to synthesize all of that, there is now strong temporal and even geochemical evidence pointing to the Hyder Pluton episode of magmatism to be responsible for gold mineralization at Golddigger and in Sherbet. So that raises a lot of suspicion towards the Hyder Pluton, which is present in much of the southern Golden Triangle. It's been systematically overlooked for the last 100 years of prospecting because it's thought to be barren. Furthermore, there are multiple lines of evidence showing that gold was mineralized in multiple phases, likely multiple pulses of one broad magmatic hydrothermal event, including higher and then lower temperature stages of gold. And that's important, of course, because that's where our high grade is being found. This also impacts the understanding of the prospectivity of Eocene magmatic centers. So that's why we have, especially towards the south, claimed a lot of extra land, which is thought to be more prospective for gold mineralization. Furthermore, the high temperature bismuth gold association found inside of the dikes and the high temperature bismuth gold association found in the multi-stage zones in the andesites sort of cast a bit more suspicion onto those dikes and help us understand what role they might be playing in the mineralization of Sherbet. So as for the plan for 2026, the name of the game is expansion. So we're going to leverage the information we have on multiple pulses and the understanding that this is an intrusion-related system to find favorable horizons, hopefully using geochemical gradients to vector towards new zones of mineralization while simultaneously expanding the ones that we already know. There's a lot of potential there. It remains open. So like I said, the name of the game is making it bigger. Every year we drill it, it gets a bit bigger, so 2026 will be no different. Anyways, thank you so much. Here's the contact information for Roger and where we're located at in Toronto. Yeah, it's been fun.